So hello, everybody. I'm happy to introduce you to Aviv, that come to talk about the inference of reinforcement learning and planning. And Aviv, the stage is yours.
Thanks, Elad. I'm very excited to virtually join the seminar. I wish I could visit, but we'll do that next time. So today I'll talk about the interface of reinforcement learning and planning. Yeah. So the topic of this talk is sequential decision making. And sequential decision problems are all around us. I'm particularly interested in robotics, and in robotics, for example, we have navigation, manipulation, locomotion. These are all problems where we make a sequence of actions, and we need to get them all right or correct in order to solve our task. But this also happens in computer systems, for example, operations research, and many, many other fields. Now, in general, there are two main popular approaches right now to sequential decision making, which are either planning or learning or reinforcement learning. And in planning, I call all the methods where you first take your problem and design some dynamical system model of your problem, and then search through this model for a sequence of actions that solve your task. So here's an example for a peer-to robot that's supposed to set up a dinner table. And we can set up a problem where the state would correspond to the robot's configuration and the configurations of objects in the scene, and so on. And now we assume that we know what happens when the robot takes an action, so how the state changes. And using that, we can just search for a sequence of actions that, say, organizes this table. Now, this is a very mature field that's been investigated under various disciplines, for example, optimal control, motion planning, task and motion planning, and many, many others. And we have off-the-shelf algorithms. We know a lot about these problems. We have guarantees and safety and theoretical guarantees about them. But there are some fundamental drawbacks when using these methods for very complex problems. So for example, one of them is that we actually need to manually design this dynamical system model, which could be very difficult in some problems. So think, for example, a robot that needs to, say, fold a shirt. I really don't want to design a state-based model for the fabric. We also need to map from the perceptions, for example, the robot's image that it sees, to this model, which could also be pretty difficult to do. And in most problems, we don't know a correct model for the dynamics. This could be challenging. And lastly, a problem that I'm going to discuss a lot in this talk is that even if we have such a model, solving it could be difficult or take a long time if the problem is complex. So think, for example, of a self-driving car. It needs to solve this problem at millisecond intervals. That's pretty challenging right now. So in other decision-making fields, we know that the best methods we have today rely less on manual modeling and more on just training deep neural networks that directly map from observations to decisions. So for example, this has been state of the art in object recognition and machine translation. And this seems like a promising approach to decision-making as well. And indeed, there's been a lot of interest in this recently. And the standard approach to this works like this. So we know that the optimal decision policy could be represented as a mapping from the robot's or agent's observation to its actions. So we can think of learning this mapping directly, just as a large, deep neural net. We need some signal for training this network. And this can come, for example, from an expert who demonstrates how to solve the task for us. It can also come from a reward. This is called reinforcement learning. And we engineer the reward to be high in the desirable outcomes of the system. Now, the beauty of this approach is that we don't model anything. We don't need to model our system. We learn directly a mapping from our observations to our actions. And deep neural networks have the capability to detect patterns in our observations that are important for solving the task. They can detect that automatically just by looking at the reward. And it's a very beautiful concept. However, there are still some problems for really making this approach work. For example, if we care about safety, a black box neural network that takes decisions is not really what we want. More importantly, whatever we learn in reinforcement learning is only what the expert or reward function taught us to do. We fundamentally cannot generalize beyond that. So we can mitigate this in some way by training on a bunch of tasks, but this is nowhere near the generalization we have in planning, where essentially every problem that I can write down in a problem description, my planner should be able to solve. And finally, as you all know, getting these methods to work requires a lot of data and time and carefully design the rewards and so on. So we see that planning and learning are two very different approaches to decision making. But let's look at humans for a second to get some inspiration. So humans definitely learn from raw sensory inputs. We learn from trial and error, from expert guidance, but we also plan. This is very clear when we make once-in-a-lifetime decisions, but we also do this every day when we try to avoid trial and error. And we definitely generalize. We can solve new problems just by looking at them without trying anything. So it seems that humans have the best of both worlds. We have the benefits both for planning and from learning. And this is great. It means that we still have some fundamental problems to solve in our field. So I asked the question how to combine ideas from planning and learning to design algorithms that are more efficient, more interpretable, and generalize better. And today I'll talk about some of the work that we did where we used structure from the planning algorithms into the learning problem. In particular, I'll talk about the question of where the neural network policies can learn to plan. And then I'll ask how we can use planning, in particular motion planning, in reinforcement learning. And finally, I'll talk about our recent work on subgoal trees, which is a new reinforcement learning formulation that's more suitable for learning planning computations. Before I begin, I would like to give you or go over some background in decision making and reinforcement learning. So the basic model in reinforcement learning is an agent that operates in some environment and tries to solve a task. And this is modeled by having the state of the environment S represent everything that goes on about the agent and the environment. The agent can take actions which change the environment state using some probability. And what the agent wants is to find some policy, a mapping from the state to its action that minimizes the sum of costs over some time horizon. And now the reason that the fact that we minimize over the sum of costs means that this is a sequential decision-making problem. We need to think at the beginning how our actions will lead us to states that will eventually lead us to higher reward or lower cost. Now, the main computational idea in reinforcement learning or underlying reinforcement learning is the idea of a value function and Bellman's principle of optimality. So the value function is a function that maps a state to the optimal cost that I can get when I start from that state. And this value function satisfies a very elegant equation called Vermont Equation, which says that the value at a state is equal to the cost at that state, the minimum of the cost of that state, and the expected value that I can get in the next state. And this can be understood in this simple path planning illustration, where if we know the shortest distance from each state to the goal, then if I'm at a particular location and I want to get to the goal, what I need to compute is the shortest distance to each neighbor plus and assume that I'm going to proceed optimally from that neighbor towards the goal. So this is the essence of this equation. All right. So now let's ask whether neural network policies can learn planning computation. And before I do that, I'm going to give you a little bit more background about convolutional neural networks. Now, these are the main workhorse of computer vision today, and they were developed as a mapping for object detection. So given an image, ask what object is in that image. And they work by having a sequence of feature detectors and dimensionality reductions. The feature detectors are just convolutions. This is taking a linear map and convolving it in the image. And then we have max pooling, which basically takes each pixel and takes the maximum within its neighborhood. And this reduces our dimensionality. Now we know that if we build a network in multiple layers and we train it on object detection tasks, these feature detectors learn to pick up useful features in our image. So for example, these would be edge detectors in the lower layers and maybe object parts in higher layers and full objects when we get to the final layer. And then all we need is a simple, fully connected linear layer to decide what is in the image. All right. So now let's talk about generalization and reinforcement learning. So we've said in the beginning that reinforcement learning just doesn't generalize. I'd like to get into that a little bit more deeper. So in RL, we learn a policy which is a mapping from our observations to our actions. So this mapping can be just the coordinate that we've just described that was designed for computer vision. Now, instead of outputting what is in the image, it outputs what action to take at each step. And we need to train this network somehow. Now, this is not a classification task. We need something to brag upon. So in reinforcement learning, this would be just the maximum or minimum of the cost that we observe in an episode. If we have an expert that gives us some data of optimal action, we can try to maximize the log likelihood of the actions in our data. The question is, in both of these cases, the expert or the reward signal tells us what to do in the domains that we've seen. But what happens if the task or the domain changes? What we need is to modify or replan. But nothing in our training algorithm or our data explicitly tells us how to do that. Now to demonstrate that this is an issue, we took what is probably the simplest reinforcement learning problem you can think of. This is called the grid world. Here there's a grid. An agent can move around this grid, and it needs to go from its position towards some goal, position shown in green here, without hitting the black obstacles. And the agent can see everything. It sees its position, it sees the whole map, it sees the goal, and we just feed in this image into a convolutional neural network, and this needs to output the action. And we train this using imitation learning and also reinforcement learning. But the thing is, we train it on a bunch of these randomly generated domains. And what we wanted to know is, after training, will it work well on a new domain that it hasn't seen before? Now, for humans, this is super simple. Just a glance is enough to understand the underlying planning computation that's required to solve these tasks. But when we tried it, we found that the agents that we trained were very good on the training domains, but failed on the test cases. They didn't understand the underlying planning computation here. They just memorized whatever they saw in the training data. So our insight to solve this problem was motivated by literature inverse optimal control and inverse reinforcement learning, where the idea that if we want the agent to plan, we can think of learning this policy as a mapping from our observation to some kind of model. We're going to plan on this model and then output an action. Now here, once the observation will change, the map will change, the model will change, and effectively our plan will change as well, and that will output a correct replanning decision. So this is great, but the question is, how can we design such a model or policy and actually how to train it? So before I explain what we did, let me describe one particular planning algorithm. And this is called value iteration. And let's think again about this grid wall domain. What we want is the shortest distance towards the goal. And we can compute it using something called a value function, which we described earlier. The value function here will represent the shortest distance from each pixel on this map towards the goal. Well, it's clear that once we have this value function, taking optimal action is clear. We just go to the neighbor that has the shortest distance towards the goal. But how do we compute it? So value iteration gives us an algorithm how to compute the value function. It proceeds iteratively. At each iteration, we go over all our states, all the pixels here, and we update the value estimate by minimizing for each state the distance to its neighbor plus our current estimate of the distance from that neighbor towards the goal. Now we're guaranteed that if we repeat this this would converge the true value function. If we have stochastic transitions, this is very similar. We just need to take the expectation over the next neighbor cost and value function. Now, when we looked at this, our observation was that this computation that we do here is actually very similar to the computation that goes on in a convolutional network, which is basically applying a filter to every pixel in the image and then doing some max pooling or min pooling. So we can actually represent the value iteration algorithm in this case as a particular type of convolute, which takes as input the current value estimate, here which is just an image of our map, and our cost for each state, which is another map, applies some convolution. The convolution takes care of this expectation over the neighbors, and then we get for each possible action a new image, and then we do min pooling over these images to get the new value function estimate, and we just plug this back as our current value and repeat. So here, value iteration is just this recurrent type of convolutional network where the weights are shared because this expectation is always the same. So this is very clear on this grid wall domain, but actually this is a more general idea because what we have in value iteration is just a linear operation followed by a minimization. And from what we know about convolutional networks, we know how to propagate through this type of computation. So with this, I've been saying that value iteration is actually a type of convolute. We went on to design what we call a value iteration network, which takes our observation and maps it first to this reward or cost function using regular convolute architecture, and then applies planning using this value iteration type of convolute, and then maps from the resulting value function towards our action. Now, because these are all familiar neural network components, it's clear that we can backpropagate with this whole planning computation. The question is what we're actually learning when we're doing this. So what we're learning is how to map our observation to a planning computation that the output of that planning computation explains either the action that we saw in our data or the reward, the high reward that we saw. Now, when we compared value iteration network to standard convolution architectures on these grid walls, they work much better. So what we show here is a success rate for different sizes of these maps. And you see that, well, in small maps, all of these networks perform quite similarly. And this makes sense because in small maps, there's not too much variation, so you can kind of remember everything that can happen. But this approach definitely doesn't scale. And once we increase the maps, standard architecture really fail, while value iterations almost don't deteriorate in performance. We can actually visualize what this network has learned. So this is an example trajectory that it predicted in red, where the blue is the actual shortest path. So it doesn't learn the shortest path, but a very short path towards the goal. And we can visualize the reward that it chose to learn for this particular map. And we see that it is high at the goal, negative on the obstacles, which makes sense, and also small negative number for all the free space. And if you think about it, this induces a short path to the goal. You want to minimize your being on these open spaces. I want to emphasize, we never gave this reward. It learned this just by observing what are good trajectories in the data. So since we've worked on this project, there's been several pretty impressive applications. So for example, Gupta et al. Used this value iteration as a component in the architecture for navigation from first-person view. And more recently, Kai et al. Used it for autonomous driving in a crowd. Another thing you can think about this work is a general idea of using a differentiable planning algorithm as some part of your neural network policy. And you can think of other planning algorithms. For example, we use it with an LQR algorithm for continuous robot control. And Lee Ho and Sinj use it for Atari games in their value prediction network, which plans a forward search on a graph. And more recently, Srinivas et al. use it in a very general kind of planning in a neural network, in universal planning networks. Okay, so right now we understand that neural networks have the fundamental capability to perform planning computations. So now we can ask whether we can use this idea to improve standard planning algorithms. And the idea here is that in many realistic scenarios, we won't solve new problems every day, we'll solve similar problems. So think, for example, of this robot in a warehouse. The warehouse usually doesn't change much. Maybe the locations or the goals of certain items change. So if we need to solve a planning problem each day in this warehouse, we should be able to kind of exploit some similarity between these problems. So here's one way to do it. So a planner takes as input some description of a problem, plans, and outputs some actions. We can replace the planner with a deep neural network, train it on many solved instances. This will take a long time. This will be offline. But then once we see a new problem, we just run a forward pass of the neural network, and it gives us immediately the actions to take in a new problem. And this will be very fast. And maybe we're going to use this to improve standard planning algorithms. So just to give you an idea that this can work in non-trivial domains, on the right is a work on learning motion planning for robotics. This is a neural network that outputs the next state for the robot given a goal. And this will train using a reinforcement learning algorithm. And you see that it can solve non-trivial planning problems without hitting these obstacles. On the left is another work on discrete domains. And this is a game called Sokoban. In Sokoban, this red agent needs to move the purple objects to the green positions, goal positions, but it can only push them. So this makes for a challenging planning problem where you need to kind of not get stuck in corners and so. So you can see that the trajectories that you need to make are not trivial. And again, you see here a neural network that was trained, in this case, using imitation learning, and it just sees an observation of the map and chooses what action to take. And at least it looks like it's doing something that is quite long-term planning. You should ask how well this works. And I can give you numbers. For example, in Sokoban, if we train on 9,000 maps, and then we evaluate on test maps that are not in the training data, we can get almost 100% success rate on one object and 87% success rate on two objects. But what does these numbers really mean? Maybe a more informative evaluation would be this. If we understand that the neural network outputs reasonable actions, it has captured some understanding of how a good plan looks like here. So we should be able to use it as a heuristic in standard planning algorithms. That will give us 100% success rate, but then we can ask, how did using this heuristic improve our planning speed or the quality of our plans? So we did this, and we compared different planning algorithms. For example, in this graph we plot on the x-axis, we show the plan lengths. This is a measure of the quality of the plan. Shorter is obviously better. And on the y-axis, which is log scaled, this is the number of states explored during search. This is how efficient our search algorithm is. And for example, the llama planner, which is an optimal planner, obviously generates the shortest plan, but it really takes a long time to get there. Feed forward, which uses an automatically generated heuristic, is much faster, but doesn't generate really good plans. A star with a neural network heuristic generated almost optimal plans, but much faster than both llama and fast forward. So this shows that the neural network really was able to learn something useful about how a good solution looks to these problems. Right, to summarize this part of the talk, our contribution here was that by thinking about the structure of the neural network, we were able to come up with network structures that have an implicit bias, inductive bias for planning computation. And we showed that we can use it to improve the generalization in reinforcement learning and imitation learning, and also for using neural networks to guide or improve standard planning algorithms. In the next part of the talk, I'm going to ask kind of the opposite question. Can we use planning to improve reinforcement learning? The motivation was for this work, this was a joint work with Siemens, and this came from the area of industrial assembly. And there's a growing trend in the industrial world for flexible assembly controllers that can quickly adapt to changes in a product. This is part of something called Industry 4.0. We would have customizable products, and we want to make the whole assembly pipeline very fast to quickly manufacture new products. Problem is that standard assembly controls right now are usually hand engineered, and this takes a really long time. And this is kind of a bottleneck in this in this idea. What we wanted to do is we wanted to design a learning-based, reinforcement learning-based assembly controller, and that can learn to assemble a product, and that would automatically account for any changes in the product design. Now, one benefit that we have in assembly or industrial problems is we know what we're going to manufacture. We have, for example, CAD models that specify the geometry of objects. So we can use planning. We can use motion planning, for example. So motion planning is an established field. We can use off-the-shelf algorithms to just figure out what is the geometric path for the assembly that we want to do. However, we still need to execute our plans. We need to control the robot. And this is challenging because our geometric model doesn't account for the dynamical properties, for example, friction or contacts, which are very frequent in assembly, and it doesn't account for pose estimation errors. And to give you an idea why this could be a problem, think about this very simple peg insertion task. We want to insert the blue peg into this hole. Now we think that the hole is in the green position, but actually it's in the red position. So our plan tells us, well, you need to go downwards, that's clear. A standard controller will tell us, well, in this position, you should push downwards. But if you do that, you'll only get stuck. What you want to do is kind of wriggle to the right and then push downwards. But that requires a much more sophisticated controller. And this is exactly what we want to avoid by learning. And just to give you an example in practice that really happens, this is an off-the-shelf planning and control package called Move It. And we applied it on this tight-fitting assembly problems. And they fail exactly where we think that they will fail in this contact point. Okay, so now you can go and say, well, let's throw reinforcement learning on this problem. This is a very common thing to do these days, but this also really won't work because you really need a very good reward function here. Otherwise, you'll never figure out a solution. So think about this insertion of this ring on this peg. If the reward was something like distance to the goal, it's clear that a robot will never figure out by randomly exploring that it needs to go up, then go away from the goal, and then insert it on the peg and go back down. It will probably just move it to the side and be done with it, and that would be a pretty good local minimum. To show that this is an issue, here's a state-of-the-art reinforcement learning algorithm on this problem. And well, this is reinforcement learning thinking it's optimal. Right? If you look at the reward trajectories, there would be nothing to indicate that this is not an optimal solution for this problem. Obviously, this is what we want. So our idea here was to combine the best of both worlds, and we did something very simple. We said, well, if we have this plan and we kind of want to follow it, let's shape the cost of the reinforcement learning algorithm to follow this plan. So we can think of the cost as a sum of distances from the plan and then apply a reinforcement learning algorithm. The point here is that because we're looking at this sum of costs, the algorithm is okay with slightly deviating from the plan, so long as that lets us get closer to the plan in later time steps. And this is the key idea here. So then we designed a system which uses the CAD model. It takes as input the geometric data. It uses the robot's perception to figure out where the objects are in the scene. it takes the goal state from the CAD models, and then uses motion planning to figure out a trajectory for these objects. And then it uses reinforcement learning, policy search, to track this trajectory. And now here we use off-the-shelf motion planning, and for reinforcement learning, we used a very efficient algorithm called iterative LQG. One particular advantage of this method was that we could initialize it with a standard tracking controller. That wasn't good enough for solving the task, but it was very good initialization to learn quickly on the robot. So here's an example of our method in practice on challenging assembly problems. Now these are all very tight fitting, less than 1 millimeter tolerance between the objects. This is done on a PR2 robot, which is not the most accurate robot you can get. And this robot also didn't have any force torque sensing. So it doesn't feel any force from the environment. The only state that it has is the joints, robot joints. So it knows where the arm is. And you can see that, for example, here, it learned to be compliant once this gear is on the peg, because that was the only way to actually get it down without getting stuck. Any other motion would just get stuck if you're in a slight angle. And this was learned using the reinforcement learning algorithm. This is fairly quick to learn. Roughly 30 minutes of interaction time. Here's a video showing that in high speed. And you can see that in the beginning, it doesn't really solve the task, but with the iteration, it gets better and better until it manages to insert this peg into the hole. In terms of numbers, we compared it to the two most relevant baselines. One is using the same motion plan, but without reinforcement learning, using an off-the-shelf controller. And the other is using the same reinforcement learning algorithm, but without the motion planning part. And you see that motion planning and, well, these baselines fail on all of the cases that we tried, except for reinforcement learning on a very particular easy instance of the peg insertion, where we start right above the hole. And in that case, you don't need to shape the reward much because it works. But all the other cases, our method was the only one that succeeded. So the main message here is that if you have even a partial plan, that's a pretty strong signal for reinforcement learning. And geometric plans are very easy to obtain in many industrial applications because you have CAD data. So you should definitely use it. All right. For the next part of the talk, I want to discuss more recent work that we did on something called sub-goal trees, which is a new reinforcement learning framework that is very suitable for learning to plan, learning neural networks that do planning computations. But let me first try to give some motivation why we actually need a new framework. So we started by saying that planners are multi-goal, so they can essentially solve every task that you give them in your domain. And that's great. But we said that we're going to have a neural network replace the planners. So, and if we train it using reinforcement learning, that's kind of a problem because reinforcement learning is a single goal. It's specified by the cost function, which is a single function. So we have distance to a particular point or something like that. So how do we mitigate this? Well, so far what we did is said, okay, let's add the goal as part of our state observation. And then that's okay, because then the goal or the cost depends on both the state and the goal. And this can work. We've seen that this can work. Question is this the optimal thing to do? And let me explain a little bit more in depth why this where there's indication that this is not really optimal. So let's think about, again, about MDPs. And let's think about this path planning problem. And let's assume we're trying to calculate the shortest distance between states on a graph. And assume that everything is deterministic right now. So applying the value iteration algorithm is actually equivalent in this case to applying the Bellman-Ford algorithm for shortest path on a graph. And this is a single goal shortest path algorithm. If you think about the complexity of running it, you need, in the worst case, if you have n nodes in the graph, you need n cubed nodes for this. But then, if you think about the multiple goal and so this is for a single goal. But what we want to reach every possible goal, then one thing we can do is, what we said is we have augment the state space to take as input both our state and the goal. And now we've increased the size of the state space by multiplied it by 2 to the power of 2. And then we can solve everything, and this everything works out. But the one with you're using Bellman forward, now we're going to do it for every goal. This is what this actually means, which would mean that we need n to the power of 4 iterations at the worst case. Now, actually, this simple trick even has a name. It's called a universal value function approximation. There's even a paper about it, and there's some interesting recent work that uses these ideas for efficient exploration and so on. But if, at least in these shortest path problems, this leads to n to the power of 4 computations, I claim that we're actually missing out on something here. Why is that? Because if we wanted to solve the all pairs shortest path problem, we can use an algorithm like Floyd-Warshall, which will give us n cubed iterations in the worst case. So what this means is that there is some structure in the problem that we can exploit here when we go to the multi-goal setting, that when we are trying to solve it in this naive way, we're actually missing out on. So what we wanted to do in this work is go back to the first principles of reinforcement learning, the Bellman equation, and say, well, can we replace the Bellman equation with a different first principle that's suitable for the all pair shortest path problem? And we wanted to develop a goal-based or multi-goal reinforcement learning framework based on that. We want to see that it has some advantage, at least theoretically, compared to the standard. And we obviously want it to be flexible enough to be used with deep networks and solve challenging problems. And I want to give to explain how we did that. So let's start from some definitions. We're going to consider deterministic problems, and we're going to consider the all pair shortest problem on a graph. So assume we have some directed graph where the weights correspond to the costs. We're going to have n nodes, and the costs are all positive, non-negative. And we're going to see that the cost from each node to itself is 0. And we're going to see that the graph is fully connected. So if there is no connection, we're just going to replace that with a very high or infinite weight connection. That's not going to change our problem. And what we want is to solve for the shortest path from each state to each other state in this graph. And what we're going to do here now is we're going to propose a dynamic programming principle for this problem that is going to be compatible with reinforcement learning or functional approximation. And the idea is based on something that we call sub-goal tree. To explain it, let's first remember what the Bellman equation would do in this case. So the Bellman equation asks for a state and a goal, what is the next state in the trajectory? And then given that state, it asks what is the next state and what is the next state and so on. In a sub-goal tree, we're going to ask a different question. We're going to ask, given a state and a goal, what is the middle state? What is the middle sub-goal between them? Given that sub-goal, we separate our trajectory into 2 segments. And now we're going to ask, what is the middle state in each one of these segments? And now, given those segments, we have now 4 sub-trajectories, and we're going to ask about the sub-goals in each one of them, and so on, until we reconstruct the trajectory. So this is a different way of thinking about how a trajectory is formed. Now we would want to write down a dynamic programming equation for this idea. So what we're going to do is first we're going to define a value function. The value function at level k is going to denote the shortest path between 2 states, S and S prime, in 2 to the power k steps or less. And this value function obeys the following equation. So first of all, at level 0, the value function is just the cost, because if you in one step, the shortest distance you can do is just go between these pair of states. That's obvious. And the value function for between a state and itself is 0 by definition. Now, a value function between S and S prime at level K is equal to finding the best subgoal with a value function of K minus 1. So basically, this means the sum of value function between K minus 1 that goes to a particular subgoal. So what this means is if we say we have a trajectory of 8 segments, we're going to separate it into the best optimal way of segmenting into 2 trajectories of length 4. So the first result is that if we apply, so this prescribes a recursive iteration for this value function. We start from level 0 and we go up and increase K. And the first theorem said that for log n, after log n iterations, we have that the value function holds the shortest path from each state to each neighbor, or for each other state in the graph. Now, if you think about how much time you need to compute this, well, at each iteration, you go over all the states, all the other states, and you minimize over the subgoals. That's n cubed, but you only have to do this log n times. So the worst case running time is n cubed log n. So this is a good indication that we're now exploiting more structure in the problem than the Bellman equation, which was worst case n to the power 4. So this is a good signal. Now we want to see some more of why it's actually good. I wanted to just say that this dependence on K is actually very important here. This makes it more of a finite horizon decision problem, equivalent. And this is what's going to help us derive some error stability guarantees next. So in reinforcement learning, one of the benefits in reinforcement learning is the use of function approximation. So if you have large states, we want to be able to generalize between these different states. And the question is how this idea of subgoal trees handles function approximation. So to answer that, we're going to define something called a subgoal tree operator, which takes as input a value function and applies this dynamic programming operation to it. And like the analysis of standard approximate dynamic programming, we're going to assume that when we do some function approximation, we're introducing errors into applying this SGT operator. And we're going to assume that the error is going to be bounded at each application by some epsilon in a uniform way, in an infinity norm. The real question here is, how does this error propagate to our final solution? So let's think about it. In our first iteration, we have some epsilon error between all of these segments. Then in the second level, we're minimizing over the value and another value so we can get at most 2 epsilon error. And then we optimize over 2 values that have 2 epsilon error, that we get at most 4 epsilon error, and so on. We only do log n iterations here, but each iteration we multiply the error by 2, so eventually we get n epsilon error for the whole for the whole graph. Let's compare this with the Bellman equation. Well, in Bellman equation, when we're close to the goal, we have epsilon. Then we only add 1. We only have one value here, so we add 1 epsilon each time. So this goes linearly, and eventually we still get an epsilon. So actually, this has the same error propagation for both of these approaches. So why are SGTs better? Well, what you need to ask afterwards is not only about the error in the value function, but how this error affects you when you're computing a trajectory using the value function. So we need to look at how we construct our trajectory and ask about that error. So if you have a value function, we're going to construct a trajectory, but by first figuring out the first subgoal. This would have the largest error, n epsilon. Then we're going to look at the intermediate subgoals, but this would have only half the error. And then the other intermediate errors, which are in shorter and shorter paths, are going to have exponentially less error. And when you sum all these errors up in the trajectory, what you get is that the error accumulation is n log n. What happens with the Bellman equation? We started the last time step. we have n epsilon. Then in the next step, we have n minus 1 epsilon, and then n minus 2 epsilon, and so on. This is a linear reduction in the error. And once you sum these up, what you get is a much worse error accumulation of n squared epsilon. And these bounds are actually tight. You can come up with worst case examples. So what this actually means is when you're using subgoal trees, you actually have less drift when you're following your trajectory, your approximate trajectory. And more conceptually, this is a very strong result. It's a very strong motivation for using subgoals in reinforcement learning. So the idea of subgoals and temporal abstractions have been there for a very long time. There are hundreds of papers on why use options and subgoals. In reinforcement learning, there's very, very few papers that show any theoretical advantage for that. The only two that I'm familiar with are written here, and they show much weaker results in the sense that if you have very particular options that satisfy some constraints, you get some improvement in the learning algorithm or the function approximation. Here we showed a very general concept. Just by looking at the all-pairs problem, the use of subgoals immediately becomes significantly more efficient. All right, so we have a new framework for approximate dynamic programming. Now what we want to do is develop some reinforcement learning algorithm that uses that. So here's one idea. This is probably the simplest thing you can think of, is doing the equivalent of fitted Q, or what you probably know as DQN. We're going to assume that we have some off-policy data, which are in the form of states and next states and the cost between them. And at each state, we're going to just sample states and goals from our data and approximate the next level in the value function by generating targets. So these are the regression targets, just the minimization of our current estimate of the value. And we're just going to do regression for fitting the new value function to these regression targets. Exactly what you do in DQN. There's an additional first step that I didn't write, where we just fit the value function to the cost and to a high cost to observation that we didn't say in the data. So what you probably need to ask here, well, this only gives me a trajectory in the state space. What about the actions that we need to take to make it happen? Well, actually, this could be easy if you have data about the actions. If you record an action between a state and S prime, then what you can learn is an inverse model using standard regression that maps from your state and your next state toward the action that makes it happen. Or you can use standard reinforcement learning algorithms to use a low-level controller, a goal-based RL algorithm that executes your trajectory, just tracks it. Let me give an example of how this works. So here's a two-dimensional continuous domain with some obstacles, and we generated data just by random states in this domain. And what we use this fitted SGT, we use the simplest function approximation we can think of. This is k nearest neighbors, just to make everything as little dependence on the actual neural network and stuff. And what you see here is the value function, the SGT value function for reaching a particular goal that is located in the top right corner. And yellow is a very high cost, meaning that it's not reachable. And you see that in the first level, well, you can only reach that point from nearby states. As you increase the levels, for example, level 6, you can reach from every point in the map, and your value function looks like a gradient flowing towards the goal, which makes sense. Here's in blue is a trajectory that our network predicted, not network, the algorithm predicted, and in green is what happens when we try to track it with an inverse model that we train from data. We also compared our approach to standard fitted Q, which have exactly the same data, exactly the same function approximation. The only difference is the underlying dynamic programming algorithm that is used. And we see that subgoal trees have much better, much lower further distance to the goal. So what happened is that subgoal trees actually learn to go towards the goal, while fitted Q just learn to wander around, never reaching the goal because of this drift. We can also measure how much it hits obstacle when trying to follow the trajectory. And here, our approach had a higher collision rate. And the reason is that this interest model that we trained is never trained to avoid obstacles. It's just trained to follow actions. And so it sometimes it would cut corners on the way. Fitted Q had a very good, strong signal of not hitting obstacles. It had the reward function or the cost function. So you just learn to kind of do nothing but never hit obstacles. And what we can also do is we can combine the fitted Q controller to follow the subgoal tree trajectory. This resulted in a much better tracking of or much better distance to the goal and less collision rate. This is just showing that we can kind of combine the approach. Right. So we see that it works. It actually corresponds with our theory that subgoal trees will be much better at these multi-goal problems. But there is a catch here. In our algorithm, we need to minimize over these states as part of our algorithm. And when you think about high-dimensional problems, this could be very challenging. So we can think of actor-critic algorithms that do this using, for example, cross-entropy methods or things like that. We're actually working on that. But let me give a different approach. You can also think of developing policy gradient-based algorithms from this idea of subgoal trees. So you can think of a policy that, given a state and a goal, predicts a midpoint in the trajectory. And then you can recursively use that to predict lower and lower levels until you reach a particular trajectory. And you can have this policy be represented using a neural network with some parameters theta, and search for parameters that minimize the expected cost over your trajectory. So we've derived the equivalent of the policy gradient theorem for subgoal trees. It looks quite similar to the standard policy gradient. You minimize the cost of a trajectory times the log likelihood, gradient of log likelihood over the probability. But once you break it down into the actual steps involved, this breaks down according to the structure of the subgoal tree, where you have the sum of the costs in each segment plus the likelihood of the midpoint in that segment. You can also add all the standard tricks that we are familiar with policy gradients, like PPO and baselines and trust regions and things like that. In the result that I'm showing you next, we used a PPO implementation of this subgoal tree policy gradient idea. So the domain was motivated by robotic motion planning. Here we had a high-dimensional problem, a 7-degree of freedom robot arm that needs to navigate in this domain, navigate between each, for example, blue start position to each red goal position. And it needs to avoid collision with itself and with this wall or other obstacles we put around. We train a neural network that takes as input the start and the goal. These are both 7-dimensional vectors, and predicts subgoals on the way. And between the subgoals, we just use linear interpolation of the motion. So it needs to kind of find subgoals that this linear interpolation will still be feasible. Here's an example of this. So here's an example, start position and the goal position. And the network first learned to predict this is a subgoal, which looks pretty reasonable. And then, this was a subgoal in between those, and this was a subgoal between these two. And you can see, for example, that a linear motion is successful for going between these points. And the last one, which seems quite far from the goal, is actually a good subgoal because linear motion is sufficient for driving towards the goal. We compared our approach with a baseline that is something very similar, all the PPO tricks and all, but uses a sequential prediction of the subgoals and not according to this tree structure. That our method was solved almost all of these problems, while the baseline had a very hard time. And here's some more examples. I said that the main point here is that we want to go for every stage to every goal. So here's an example of these trajectories from different starting states and different goals. And you see that it can learn quite interesting motions. Right, to conclude, we suggested a new reinforcement learning framework and with very different first principles. Instead of looking at MDPs, we're looking at the all pairs shortest path problem. And we can prove that this is more efficient, fundamentally more efficient in a multi-goal setting in handling function approximation. Now it can be a basis for many, many new algorithms. I've shown you pulse gradients and fitted queue. We're now working on actor critic algorithms, but I think that there are much more that we can do here. And some questions that we're going to explore in the future work. First one is, well, everything that I said right now holds for deterministic systems. How to make this work in stochastic systems is more challenging. One thing we can do is we can update our plan online using an MPC algorithm that replans, but there's much more to explore. How to do exploration here is very interesting, and to handle high-dimensional observation like images is a significant challenge. All right, so thank you all for listening. I'd like to thank the many collaborators on these projects, and I'll be happy to answer any questions. I think you are on mute.
I have a question. How does the learning to plan correspond with the model-based approaches of RL?
In what sense?
Like when you learn the model of the world in parallel of learning the value functions, like in model-based approaches, how does this relate to learning to plan?
So in learning to plan, in the approaches that I showed here, we assume that we know, or when we combine learning to plan with the planners already have a model of the world. So they're not learning anything about the model. They're just trying to learn how to plan faster. In model-based RL, there are two challenges. One is, how do you learn an accurate enough model that planning on it will actually give you something feasible, and also how to plan efficiently using that model. So I think AlphaGo, for example, or AlphaGo 0 is a good combination of an algorithm that learns to plan. It combines MCTS with value function learning, but it relies on the world model, the accurate model of the world. There's more recent versions like U0 that also learns the model concurrently. But these are two very different problems. So for some problems, it's very difficult to learn an accurate model of the world. And for example, think about image-based observations or learning to fold claws or ropes and things like that. So we have different works that try to solve the model-based learning problem. But what I showed you here, we're assuming that we know the model. We're just trying to learn how to plan faster. Is that what you meant?
Yeah, so this could be possibly to integrate learning to plan within a model-based reinforcement learning.
Exactly,
so
yes, exactly. And yeah, exactly.
So have you showed example where both of them play together? Like
no, so far we've investigated in separate, but we have works that, well, most of the problems that we've looked at either complex planning problems with, or simple applying problems with high dimensional observation where you need to, learning a model would be challenging, but planning is relatively simple. I think one work that tries to attract that from DeepMind is the Mu0 recent work, but applying that to problems where identifying the model is really complex, I think that's one of the challenges that we don't yet know how to solve as a community well, and many people are, including us, are working on.
So learning to plan is focused on that value iteration is just not efficient, right?
Value iteration or other planning algorithms. There are many planning algorithms that are.
Yeah. Okay.
Think, for example, a good example would be autonomous driving. In autonomous driving, you usually have a model of the planning problem, but it's a pretty complex problem that you want to do very quickly online. So you'd want to integrate some intuition about how a good solution looks like to make your planning more efficient. And this is where we come in.
Okay, thank you.
Okay, so thank you, Aviv, again for coming and giving this great talk.
Elad, will this be available online?
Yes, it will be in Panopto, and I can send you the link for that.
Yeah, I'll be
Great,
happy.
thanks.
Thank you. Great
Okay.
talk, Aviv.
Thank you very much.
Thank you, Aviv.
Anyway.
Thank you.